Welcome to The Explainer. Today, we're diving into the totally fascinating economic forces that dictate why the wildly powerful devices we use every single day just keep getting cheaper. We're going to look under the hood of the microchip industry to see the hidden math that basically runs our modern world. Let's start off with a massive paradox, right? How is it that we carry supercomputers in our pockets that actually cost less than the bulky, incredibly weak mainframes of the past that used to cost millions of dollars? It kind of defies basic economic logic. Usually, better performance means a higher price tag, but in computing, the rules are completely inverted.
Here's our roadmap for this explainer. We're going to cover the price versus cost paradox, the anatomy of chip manufacturing, the math of die yield, why volume drives down price, Moore's law and scaling, and finally, the price-performance balance. Let's get right into it.
Section 1. The price versus cost paradox. Uncovering hidden costs. Okay, let's break down what actually makes up the price of a computer. Because the relationship between cost and price is surprisingly complex. You might actually be shocked to learn this, but the raw component cost, meaning the actual physical materials that designers buy, makes up only 40 to 50% of a product's final list price. Yeah, literally half or even more of what you're paying at the electronics store has absolutely nothing to do with the physical silicon, the wiring, or the plastic. Crazy, right? When you really look at how costs stack up across different computer classes, the direct hardware costs are just the baseline. Stacking heavily on top of that is the gross margin. We're talking about all that non-recurring brainpower and overhead here. R&D, marketing, equipment maintenance, taxes. These upfront fixed costs take up a massive chunk of the final price. Figuring out how to shrink that overhead is the absolute secret to affordable tech. Moving to Section 2, Anatomy of Chip Manufacturing, from wafer to chip. To understand how we actually lower those massive overhead costs, we need to get physical and see how chips are built from the ground up. The integrated circuit manufacturing process is an absolute feat of engineering, and it goes through 4 main stages. First up, a giant cylindrical silicon wafer is grown and tested. Second, that wafer gets chopped up into tiny individual squares, which we call dies. Third, those tiny dies are packaged into the familiar chips you and I recognize. And finally, the whole completed chip undergoes rigorous testing. Now, because you're trying to fit square areas, the dies containing all the circuits, onto a perfectly circular wafer, you inevitably end up with what's called the wafer waste. That's basically the waste in silicon around the round periphery that just can't be used. So efficiency here is literally everything. Which brings us right to Section 3, the math of die yield component survival. Since our wafers are now chopped, let's see how this builds into some crucial math, because, well, not every piece of silicon survives this microscopic chopping process. The absolute crucial point here is die yield. No manufacturing process is completely perfect, especially when we're dealing with microscopic components measured in fractions of a human hair. So die yield is the strict percentage of manufactured components, the good dies on a wafer, that actually survive and work when they're tested. If your yield is low, you're throwing away a ton of expensive silicon, and your costs just skyrocket. There's a core equation that acts as the secret to basically everything here. The cost of a single die equals the cost of the whole wafer divided by the total number of dies per wafer, multiplied by that die yield we just talked about. So if you want to shrink your cost per die, you really only have 2 options: squeeze more dies onto the wafer, or make sure a higher percentage of them actually work. All right, Section 4, why volume drives down price, the magic of scale. This right here is the core focus of our explainer. How does massive volume act as the ultimate equalizer for price? Why does pumping out millions more of a chip radically drop its cost? Remember those massive non-recurring overhead costs we talked about earlier? The billions spent on R&D to design the chip, the insanely expensive equipment to print them, those are fixed. Imagine if you only manufactured 10 microchips. Those 10 chips would have to absorb billions of dollars in R&D, meaning they'd cost hundreds of millions of dollars each. Obviously, no one is buying that. But if you manufacture 10 billion microchips, those exact same fixed R&D costs are spread incredibly thin. The brainpower cost per chip drops to essentially 0. The data explicitly proves this. Volume is the magic bullet. When you exponentially increase the volume of chipset manufacturing, you directly decrease the list price. Not only are you spreading out those non-recurring R&D costs, but you're also drastically improving your purchasing efficiency for the recurring raw materials.
When you buy silicon and wiring in unprecedented bulk, economies of scale kick in hard, driving those direct component costs down even further. It's a massive win.
Next up is Section 5, Moore's Law and Scaling, making things smaller. But volume doesn't act in a vacuum. It is fundamentally turbocharged by physical scaling. We aren't just making more chips, we're making the components on those chips vanishingly small. Looking at the timeline of computer generations, there's a relentless historical trend. We started with bulky glass vacuum tubes in the 1940s that failed constantly. Then we moved to single transistors in the late 50s, to medium-scale integration, and finally to very large-scale integration from 1978 onwards. This evolution allowed us to fit thousands and eventually billions of devices onto a single chip. By shrinking the feature size, which dropped from a comparatively massive 10 microns in 1971 down to 0.18 microns in 2001, and obviously much further today, Moore's law dictates that we can fit exponentially more dies on a single wafer. This literally multiplies the volume effect. Because the components are so incredibly tiny, you get a quadratic rise in the transistor count, and the cost of an actual logic gate approaches zero. Plus, because the electrical path length is shorter, performance naturally increases linearly while power requirements drop.
Section 6, the price-performance balance, engineering trade-offs. Finally, let's look at the delicate art of design, where engineers have to balance all these extreme economic and physical factors to give us the products we actually use.
You can't just keep adding transistors endlessly and expect linear returns. Engineers face strict physical limits, like Pollock's rule. This states that the performance increase is roughly proportional to the square root of the increase in complexity. So actually, scratch the idea that more is always better. Simply doubling a processor's logic complexity only gives you about 40% more performance. Just cramming more transistors in isn't enough. It requires incredibly strategic architectural planning to actually make it worth the cost. Designers are constantly walking this tightrope. At the high-performance extreme, like with supercomputers, they'll sacrifice cost entirely just to hit those crazy speed targets. At the low-cost extreme, say embedded microcontrollers in your washing machine, they sacrifice performance to keep it dirt cheap. The sweet spot, where the designer perfectly balances the volume economics of silicon against user performance demands, is exactly what powers the modern PC and server market. But at the end of the day, no matter how cheap the manufacturing gets or how dense the silicon is, the ultimate value of these high-volume chips is measured by one single thing: execution time. That is the real measure. Good benchmarks and execution time dictate whether all that brilliant engineering and volume scaling actually translates into a machine that feels fast to the end user.
So, this leaves us with a massive, fascinating question for the future. As we hit the physical limits of power density and the traditional clock speed scaling of Moore's law starts to level off, the industry is shifting to massive multi-core and GPU architectures. Will the immense economic power of volume manufacturing be enough to adapt and save this next generation of computing from becoming prohibitively expensive? It is definitely something to think about the next time you're holding a miraculously cheap supercomputer right in the palm of your hand. Thanks for hanging out with me for this explainer. Keep wondering, and I'll catch you next time.